Welcome to the electrostatics lesson on electric fields. Let's begin our discussion here with a drawing that has a large positive charge here on the right. We'll call it for now Q1, and a test charge that we'll put out here, and you can label it at some distance R away from the large positive charge. We'll call that charge Q2. The first thing we're going to talk about is direction of electric field, defined to be the direction a test charge would take in that field. To be a test charge, you have to meet two requirements. One is that you are positive, and the second is that you are small relative to the charge that you are determining the electric field for or other electrical quantity. So to be small and to be positive. Sometimes we get redundant and we say positive test charge. We don't need to say that, but it is a reminder to us that test charges are positive and are used to determine direction of electric fields. In this particular case, what direction would this test charge travel relative to this large positive charge over here? And of course, you understand by now that this large positive would repel a test charge in that direction right there, and so we would say that that is the direction of the electric field itself. So wrapping that up, direction of electric field defined to be the direction a test charge would take in that field. Let's move on to magnitude. To talk about magnitude, the strength of the electric field, capital E, is equal to the strength of the electrostatic force divided by the charge. To be more specific, it's the strength of the the electrostatic force at that spot divided by the charge. Well, if we take, how would we calculate in this instance the strength of the electrostatic force? Well, you know from before that we would use Coulomb's law to do that. K, Q1, Q2 over R squared. The question becomes, which charge do we substitute in the denominator of this equation? Well, going back to the definition of magnitude of electric field, the strength of the electrostatic force at that spot divided by, it would be the charge located at that spot. So in our example above, the charge that we would substitute in the denominator here would be the charge located at that spot we want to know the strength of the electric field at, and that charge would be Q2. Clearly what you see here is a double fraction, so we're going to simplify that double fraction by multiplying both the numerator and denominator by the reciprocal of the denominator. And when we simplify that, you can see that what we get left over is KQ1 over R squared. If we say that Q1 is the larger charge over here to the right, we can abbreviate that K big Q over R squared as a reminder that the Q in that equation is the source of the charge itself. This derivation is nice because what this means is you don't need to know the value of the charge at the location that you want to know the strength of the electric field at. All you need to know is the charge of the source, and you need to know the distance from that source. And as long as you know those two things, you can calculate the electric field strength without knowing the charge at that location. All right, let's move on to how to draw electric fields. This often is asked of you in the exam. And let's start with the shape of an electric field for a single positive unit charge. This could be a point charge that's positive. It could be a sphere that has a positive charge, in other words, an absence of electrons on it. And either way, it is a single positive charge, and we want to know what the shape of the electric field looks like for that single positive charge. Well, what we do is we start with a test charge, and we decide where would we put our test charges to draw and indicate the shape of that electric field. Well, since our source charge is positive and test charges are positive, we would start with our test charges close to that source. And our general rule of thumb is that we would draw 8 test charges, one on the top, one on the bottom, one on the right, one on the left, and 45 degrees in between for a total of 8. And then you simply draw a line that represents what each of those test charges would do due to the source charge itself. And it's clear that in each of these cases, every test charge would travel in a direction that is straight away from that source. It is also clear to us that the strength of this electric field gets weaker the further away you go away from that source. This is verified both from the equation itself, but you can also tell that the strength of any field is strongest where the lines are most concentrated. And the lines are most concentrated near the source of charge, and they get and diverge further away from each other the further away you get from that source. So the strength of the electric field weakens the further you get away from the source. Let's move next to a single negative charge. And of course, what we would do here, with your paper being the limit, you would say that your paper, the limit of your paper represents infinity, is that we would want to start with our test charges far away from that source, since our test charges would be attracted to a negative. We draw our 8 test charges, and we draw what would happen. This diagram, essentially, this electric field or electric field map, is opposite of the one we just previously drew. Lines are straight, but arrowheads are pointed in the opposite direction. Okay, next, let's draw the shape of the electric field for a pair of positive charges. Our test charges would start near each one. So we draw 8 test charges near each source, and we draw what would happen as a result of that. We only end up with 2 straight lines in this map, and they are the ones on the right-hand side and on the left-hand side. Every other line is curved because as this test charge, for example, moves away from this source, it gets repelled by that source and also repelled from the other one, giving it a curved path. This line also gets double repulsion, but in a straight line path, as does this field line over here. Line of force is straight on the left as well. Let's talk about these 3 points I've added to this diagram, points A, B, and C. Describe the motion of the test charge as it moves from A to B to C. Well, clearly, we understand that the speed of this test charge would increase as it traveled to the right. But what's unique about this is that it does so with decreasing acceleration. This is counterintuitive of what we learned in kinematics. When we hear decreasing acceleration, we think that the object slowed down. In this particular case, all decreasing acceleration means the rate at which it's speeding up decreases. This is, of course, because if you compare the force at A to the force of B to the force of C, the further away you get, the weaker the force becomes. If the weaker the force, that means the acceleration is going down, F equals ma. However, this charge does continue to increase in speed. So we say that it increases in speed at a decreasing rate of change in speed. Next, we'll draw the electric map, the electric field lines, electric lines of force for 2 negatives. We start with our test charges far away, within the limit of your paper. And once again, these field lines look similar to the previous ones, but with opposite arrowhead directions. Something important to note here if we're comparing the motion of this test charge at A, B, and C this time, we understand that it would increase in speed, but this time it increases in speed with increasing acceleration. So the rate at which it speeds up increases. And you can see, of course, this is because as you move from A to B to C, the force increases, therefore the acceleration increases, and therefore the rate at which the charge speeds up also increases. All right. Let's move on to, I believe, 2 more electrostatic scenarios here. This is unique because this is called an electric dipole. An electric dipole is 2 charges that are equal in magnitude but opposite in sign. You should indicate on your diagram a key here. I've used solid red lines to represent lines of force, also called field lines. And my dashed black lines are called equipotential lines. We'll get to that in a minute. Let's first deal with our test charges and creating the lines of force. We have 8 near our positive, and we have 8 far away from our negative. Note that the test charge here close to this positive also serves as the one that's far away from the negative on the left-hand side. That test charge would go straight over to this negative. This test charge would go straight into this negative. And this test charge would go straight away from this positive. All the rest of the field lines are curved, and all curve away from the positive toward the negative. If we said that this source charge over here has a charge of positive 4 volts, sorry, misspoke, has a potential of positive 4 volts, and that this negative over here has a potential of negative 4 volts, it makes sense to us intuitively that there would be a line down the middle through which that there would be no potential at all. In other words, that's equal all along this line. And we would say that the potential at this spot is 0 volts because you're midway between positive 4 and negative 4. Note that I've done my best here to draw this equipotential line not only straight, but that it falls perpendicular to each line of force as we go. If we draw our next one representing positive 1 volts, you notice that it starts to curve as you maintain the fact that it's perpendicular to the lines of force. Likewise, the positive 2 volts and the positive 3 volts. Same on the other side with our negative lines of equipotential. Okay? So here we have negative 1 volt, negative 2 volts, and negative 3 volts. And what you end up discovering here is that the potential difference between these 2 charges, either way you go, if you go negative 4 minus positive 4, that is a potential difference of negative 8. Well, if you start at that negative charge, 1, 2, 3, 4, 5, 6, 7, 8. So you cross 8 lines, equipotential lines of whole number in order to get back to the positive charge, giving you a potential difference of 8 volts. Also keep in mind that there are also other equipotential lines in between these. We're just not drawing them. Okay? Lastly, if we take a look at our last electrostatic scenario, we have parallel plates that are connected by a potential difference. The top plate connected to the positive terminal and the bottom connected to the negative terminal. This makes the top plate positive and the bottom plate negative. We would put our test charges closest to a positive and furthest away from the negative. We're concerned about the electric field inside, in between the plates. And you can see as each of these test charges would be repelled by the positive, the electric field is the same everywhere between the plates. And that electric field is calculated by the potential difference between the plates divided by the plate separation, D.